see my whiteboard? Yes or no?
Yes.
Okay. The first topic, well, the only topic that we study today is determinant. Determinant is another approach for the solution. So we studied last time solving the system, linear system using matrices, no? However, I want to study another approach against determinant. What is that? Well, determinant is a little bit weird to the definition. Some book call, okay, this is the function, such that the domain of that function is the set of the square matrix and the domain or the range, sorry, is all real number. So what is the idea there? All real number. The range is all real number. Okay, so now what is the idea? Well, when you compute something, it's called a determinant to only one square matrix. What means square matrix? Well, it's a matrix 2 by 2 maybe. So we have 2 times 2 is 4 element. Let me want to call A11, A12, A13, A13, no, A21, sorry, A22. This double subscript A22, for example, indicate this first is a row. Okay, you have, for example, you have in the second row, and the second subscript is a column, no, column. It's a column. It indicates the position. This is 2 by 2 for entry, for element, for number. However, 3 by 3 is 9. Is A11, A12, A13. Remember, the first subscript indicates the row 1, element 1, column 1, row 1, column 2, row 1, column 3. So this, the name of this is 21, 22, and 23. Jose Cabrera is having trouble by logging. Oh, hi. You always are early. A31, A32, and A33. And so, but basically, the most important thing you need to understand is okay, when you compute the determinant, you compute it only in the square matrix, never in rectangular. O sea, for example, rectangular 2 by 3, no? 2 by 3, A11, A12, A13, A21, A23, 22, sorry, 22, A23. Bueno, es rectangular, ¿no? Because the dimension is different, it's 2 rows and 3 columns, it's no determinant. At least in these undergraduate classes, not define the determinant for a rectangle, only for the square, okay? And you see the formula, and you see the interpretation, you see everything. So far, do you follow me? Oh, let me see attendance. Okay, a lot of people. Sebastian, Janice, Daniel, Gustavo, Jonathan, Michael, Guadalupe, David, Rebecca, okay. Samiha, Destiny, Giselle, okay. So far, everyone follow me the basic idea? Okay, so now what is the interpretation? What is that? What is that? How you compute that? Well, the interpretation is it's complicated to understand, at least for me. Look, the computation is, look, and the email I sent today, I sent the PowerPoint, I have this slide. Exactly the same slide that I put here in my webboard. So the formula to compute the one determinant 2 by 2 is super easy. You have two diagonals, and the diagonal is, you know, you multiply a times d. So we have two diagonals, the upper and the lower, whatever you want to call, but you multiply the main, the most important diagonal is a times d, is ad, and in this case you assume that the sign is exactly the same of the sign that you obtain after the multiplication. So you multiply a times d, stay the same sign, and c times b and opposite sign. Well, no, actually, it's like it multiplied by extra negative one. So this is like a one extra, one negative one extra, and this is positive one. You know, the positive one is invisible. No? One example to understand. So, as you want to compute this determinant 2 by 2, well, we multiply 4 times 6 is 24. And 2 times 1, but in this case change the sign, negative 1 and negative 2, the answer is 22. Cool? It's the formula, guys. What is the, do you understand the formula? Do you understand the idea? It's 2 by 2, no always says like that. It's only in 2 by 2, and 3 by 3 more complicated. Do you follow me, the idea? Say something. Yes. Cool. You said it's a yes. Okay, now, what means 22? What means 22? What is the interpretation of 22? What represents 22? 22 what? Okay, so one idea is you suppose que in the determinant, look, we have a vector, row vector is, for example, 4, 1, and you have another row vector that is 2, 6. And you consider like vectors, and you add in vectors exactly the same you are doing in physics or in trigonometric class. So MAC1140. So say you are in the component by component, 4 plus 2 is 6, you get the vector, and 1 plus 6 is 7, okay? So now it's a vector, okay? And now, how do you know that? Geometrically, look at that. Geometrically, you have two vectors. Look, you have two vectors. Okay, this vector would be, are you familiar with the notation of the vector in trigonometry or physics? Is 4, 2 using angular bracket, or using univectors as 4i plus 2j, using the univector I and j, no? And the second vector is 2,6. No? However, when you add in the vector using the parallelogram rules, we have another vector. Okay, this vector was the vector 6,7. No? 6,7, que was the answer of this vector b1 and this vector b2. No? And you obtain one parallelogram because you adding the vector using the parallelogram rule, or yeah, it's a name, technical name, and the area of the parallelogram is 22. I want to prove right now, okay, 22. So this is the interpretation. So when you compare the determinant 2 by 2, when you compare the determinant 2 by 2, the answer is given, 22, is the area of the one parallelogram formed by these two vectors. Okay. Okay, you remember, for example, the addition. Okay, I have another slider here. Okay, you see more clear. So this is the, for example, we come back again to the parallelogram in green color 22, but you can compute it, or you can verify, you can prove. Okay, this is 22 when you, for example, you multiply the area of this rectangular, of course, is 6 times 7, okay, 42. and you're subtracting the brown part. Okay, the brown part is, you know, this is 10. 2 plus 2 is 4, plus 6 is 10. And here is another 10, and 10 plus 10 is 20. And you're subtracting 20 is 22. Okay, well, geometrically speaking, the area, so it's a little bit, you say, what is the formula? I don't know. Well, the formula for the parallelogram in geometry we studied in the high school is the length of the base multiplied by height. But you have no idea what is the height. Well, the length is one vector que you suppose. However, si you encrypt this parallelogram in one rectangular, in which I know that the dimension is 6 and 7, the total area is 42, that one. And the part I don't want, I don't care, is the brown part is 20. So 42 minus 20 is 22. So conclusion, the most important thing you need to understand so far is determine. We have a specific formula, que es the multiplication of the diagonal, and so basically, when you face one problem, we are doing a lot of problems right now. One determinant, 4, 2, 1, 6. Oh, it's easy, Professor. You multiply that. Go ahead.
So it's kind of like making a trapezoid, you said?
No. I never talking about trapezoid. So we have parallelogram.
Yeah, parallelogram, sorry.
In green color.
So the middle I forgot what the lines are called. Vertex?
Yeah, vertex, yes.
Yeah, the middle vertex is the combination of the two.
Yes. Yeah,
okay.
Okay, so now the most important is you don't need to prove anything. Only, what is the formula? The formula you multiply 4 times 6, 24. This and this together, 24. And keep positive number. And 2 times 1 is 2. And you're subtracting, and the answer is 22. What is the interpretation of this 22? The interpretation of this 22 is when you plot the vectors. Okay, the first vector is 4, 1. 1, 2, 3, 4. 1. This is my first vector. And my second vector is 2, 6. 2, 6. 1, 2, 3, 4, 5, 6. Okay. Therefore, you form it. Sorry. But Control Z. You connecting the origin, of course, to the point. And when you add in this vector using the parallelogram rule, very similar to the thing we are doing trigonometric, the area of this parallelogram is 22. It's exactly the same. The answer can give me the formula for the determinant. Cool? So far clear? So far clear?
Yes.
Cool. Let's move on to the 3 by 3. 3 by 3 is very complicated. Very. Let me try to do my best to explain 3 by 3 determinant. Okay, let me try. Let me try. Here, I separate this. And enlarge this, zoom in. So now we have a complicated problem because, 3 by 3 determinant has 9 elements. 3 times 3 is 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So now we're using another formula que is more general for a more dimension. This formula I want to explain now in 3 by 3 is the same formula, but of course too long, for the 4 by 4, 5 by 5, and so on. But the formula includes two new ideas: minors, and cofactors. What is that? What is minors? Suppose that you need to find the minor 1, 1. The minor 1, 1 is the new determinant. It's smaller than the original. When you delete the row 1 and the column 1. So when you simultaneously delete row 1 and column 1, guess the number here, 1, 1, 1, 1. You obtain new determinant. In this case, it's reduced the dimension for the determinant. So the original is 3 by 3. When you delete 1 row, 1 column, now you have 2 by 2. Okay? Entonces es relatively easy. Let's see in the sample, but this is the definition of the minors. And what about cofactor? Well, cofactor is the same thing of the minor, except the size. So the sign is, look, this is a little bit complicated to understand, but I try. It's -1 raised to the I plus j minor ij. What is that? So cofactor ij, let me using the proper terminology. Cofactor C, capital C is cofactor ij. Suppose cofactor 1, 1 is equal, and this -1 exponent I plus j is alternating sign, is plus minus, plus minus. Sometimes plus, see this part is even number. And of course, yes, odd number, no, is -1. Entonces, there are many ways, easy way, not complicated. This formula is definition, pero es easy. For example, suppose the cofactor 1, 1 is equal to -1 raised to the 1 plus 1, que obviously es 2. Y 1 plus 1 is 2, es -1 square. And -1 square es +1. Entonces, +1. Entonces, I erase because +1 is invisible. Entonces, we have the minor 1, 1. Different situation happen, cofactor 1, 2. Cofactor 1, 2 is -1 raised to the 1 plus 2, or 1 plus 2 is 3. And -1 to the third power is -1. Okay, entonces now you replace by -1, minor 1, 2, and so on, and so on. Entonces es relatively easy without formula to understand that, for example, the sign of the cofactors is positive, negative, positive, negative, positive, negative, positive, negative, and positive. Okay, suppose the conclusion, the cofactor 1, 1 is equal minus 1, 1. The cofactor 1, 2 is -1 minus 1, 2. Because this negative. So I am talking about the first one is this. And the second is negative is this. Okay, now cofactor 1, 3 is positive, minus 1, 3. And so on. So we can, the beauty of this is to compute the determinant, we can using any row or any column. Wow, this is the new thing that bring me the determinant. So in matrix, we always working with the row operation, row operation, row operation. Never using the column. Bueno, you use it, pero no directly. Entonces now in the determinant, no. In the determinant, we use row or column. Column 1, column 2, or column 3. So what the thing I try to explain is that you can expand using the formula I want to explain in a few seconds, using any row or any column. Suppose another student select the column 2. So you're using this, you're using this, I'm using this. And magically, guys, the answer doesn't change. It's the same. Let's do one example and clarify this. But don't worry too much, because after I want to explain how you compute this using the software. The software is fantastic. Okay, look. Suppose I want, let me make it zoom. Compute that determinant. It's given at the beginning. is 3 by 3. So 3 row. Remember the first number indicate the row, 1, 1, 1. And then the second number indicate the column, 1, 1, 1, 1, 2, 3. Okay, so now you take the formula say, cofactor formula, say. For example, I make a decision, expand the determinant using these. Another student using another row or another column, and the answer unbelievable doesn't change. Now the formula say C11, no, sorry, no C11. The formula says, yes, A11 multiplication by C11 plus A12 multiplication by C12 plus A13 multiplication by 1, 3. Okay, so what is A11? A11 is 1. That's the first entry. Who is A12? Well, A12 is the second element, is this. Because I make a decision, I repeat one more time, to select the row 1 to expand the determinant. Likewise, A13 is this, okay, 2. Okay. Then the complicated part is not A11, A12, and A13. The complicated part, not complicated, but a little bit more not clear, is who is the cofactor. Well, the cofactor is the minor. So actually, I delete. Look at that. This is an important moment. You delete mentally. Suppose I want to compare the cofactor 1, 1. Cofactor 1, 1, you delete mentally this row and this column. And stay alive. This determinant gets 2 by 1. And I copy here. This is a cofactor 1, 1. Cool? Likewise. Suppose now, cofactor 1, 2. Cofactor 1, 2 is the cofactor that you obtain when you, actually is cofactor 1, 2 is equal minor 1, 2, but it's negative, no? That is the reason I put a negative. This negative indicates this negative. But a minor is you delete mentally, you delete the row 1 and column 2. And stay alive 3, 1, 1, 3. 3, 1, 1, 3. Okay, and this is this cofactor 1 to include the sign. So the first one was positive, the second was negative, and the third one obviously is positive. To say you A13 is 2. A13 is 2. Let me see. A13 is 2, no? It's 2. Why? Because it's that number, right? A13. And the cofactor 1,3 is the cofactor 1,3 is the minor 1,3 is positive. Now you delete mentally the row 1 and the column 3 and stay 3, 2, 1, 3, 2, 1, 3 is exactly this determinant. Okay, now I finish. No, because the only thing that you are doing in the formula is you have a complicated determinant. Okay, 3 by 3, and you convert in several 2 by 2. Now 2 by 2 is piece okay. With 2 by 2 as you multiply this time this is 6. This time this is negative 3. This time this is 3. 3 times 3, sorry, is 9. This time this is 1, but it's negative. Remember that diagonal is positive. That diagonal is negative. This is the rule. So now we multiply this is positive is 9, and this is 2, negative. And don't forget one of the coefficients here is 1, because this coefficient is this one. Here is negative 1 according to the position of the cofactor. And this is 2, and this 2 is this 2. Okay, now the rest is multiplication. Let me try. 6 minus 3 obviously is 3. Minus 9 minus 1 is 8. So that's minus 8. The answer of that part including the sign is minus 8. And 9 minus 2 is 7. Times 2, 14 positive. And the answer is 9. Boom. Do you understand the idea, guys? A little bit complicated, huh? Opinion, come on. Wow. Somebody change the view. He said you don't like that view. Question. No? Everyone follow me?
Yeah, I have a question. Why did the second equation change to negative?
It's according to the position for the. Good question. It's according to the position of the cofactor. Let me explain one more time. In different way, of course. Look, remember que the cofactor ij is equal -1 raised to the I plus j, sorry, multiplied by minus yij. So for example, in the 3 by 3, the sign gets that part is positive here, minus here, positive here. See, I make a decision to expand using that row. It's obvious that the first guy is positive.
So the middle is always negative?
No. So you make a decision, for example, expand using the second row to say negative, positive, negative. And you make a decision to expand using the third row, a positive, minus, positive. But you remember you can use in any row or any column. And the beauty is que the answer stays the same. Okay, in this case, well, I need to make a decision. Frequently, still using the row one, but not always. Yes, let's see example more complicated. It's better select another row.
Okay, I got it. Thank you.
Okay, cool. Now, okay, so what is the interpretation of the 3-dimension 3 by 3 determinant? Because in the 2-dimension is the area inside the parallelogram. However, in 3D, the interpretation is, let me see. Ooh, look at that. That slider. Let me make it zoom. Okay, in this case, obviously, we have 3 vectors. 3 vectors. And 3 vector in 3-dimension space is representing like that. Look at that. 1 vector, 2 vector, 3 vector. And when you format these 3 vector, we can generate a parallelepiped, no parallelogram, parallelepiped. I don't know if the spelling is correct. Parallelepiped. What is parallelepiped? What a parallelepiped is like a box. But this box, suppose that you have one vector here, another vector here, another vector here, another vector here. So 2 vector original, 1 vector here, and you create a parallelepiped that is a box. But it's a box that the edge of the box are a little bit sloping, no? So it's inclination, no? And the volume inside, so the capacity of this is the answer of the determinant 3 by 3. In this case was 9. 9 something, I don't know, liter. Cubic meter, it's volume, it's capacity, it's the interpretation. So when you compute determinant 2 by 2, the number that you obtain is the area of the parallelogram. However, when you compute a 3 by 3, you obtain the volume inside the parallelepiped. Okay, and it's the same idea of the in 2D. In 2D, we have the classical rectangular, but we have a parallelogram, and you have inclination. It's in 2D. In 3D, we have the classical prism or cubic when the angle is 90 degrees. Nice. But this case is not 90 degrees, it's arbitrary angle. But it's also boxes. The technical name is parallelepiped, no? But it's the area inside. Cool? This is the interpretation. So somebody asks you, what means this number? Well, no, this is the volume of the one parallelepiped. Okay, do you understand this or no? Let me try now to study in detail the property of the determinant before doing example and application of this. Let me try to study some property, important properties. Okay, the first property is this. Let me show you. This is the value of the determinant change the sign if any row or column are interchanged. Okay, what means that? Suppose that you have the original determinant 3, 4, 1, 2. Okay, by the way, you multiply this as 6. You multiply this as -4. Remember, when you multiply, the diagonal gets going up and negative. Entonces 6 minus 4 is 2. Okay. However, I want to change something. I want to permutation, interchange. For example, in this case, I did, okay, this is row 1. So row 1, interchange row 2. Let me try it. Row 1 is 3, 4. I put here, bottom, and 1, 2, I put in the top. So the thing I did was, in this, the transformation from this to this is interchange, swap, row 1, row 2. Entonces, bueno, okay. Entonces, what is the action? Well, the action is that when you multiply now, according to the formula that you know, you multiply this and this first, a 4, positive, and this and this is negative, 6. And the answer is -2. Wow, entonces the answer is the same value in absolute value, but opposite sign. Keep in mind, when you permutation, swap 2 row or 2 column, so see you, for example, column 1 swap to the column 2, similar situation happen. Look, let me show you. The thing I did from this to this was the column is 3, 1, 3, 1, the original 4, 2. However, here I write differently. I write 3, 1 like a column. This is the column 1. This is the column 2. And the next version, we have 4, 2, and 3, 1. So the only thing I did was interchange this column to this column. No? And when you compute again, the determinant is 4 positive, no x positive, and -6. Okay, answer is -2. So in conclusion, suppose I have a big, which I illustrate quickly using 2 by 2 because it's super easy. But see, you have another determinant 3 by 3, 4 by 4, 5 by 5, and you permutation 2 column or 2 row, you obtain the same value but opposite sign. I guarantee you 100%. You follow me? This is the first property. Okay. The second property is obvious, it's elementary, is if all entry is the technical name to call the element inside. So entry is A11 or A12 and so on. If all the entry in any row or columns are 0, suppose one determinant gets 0, 0 here or 0, 0 here. It's obvious that the answer is 0, no? Because you multiply 0 times 2 is 0 and 4 times 0. In this case, it's obvious, but in all the big determinant, suppose 7 by 7, you need to see what the answer of this. And you visualize, okay, 1 column 4, for example, is just 0. Oh, so not necessarily compute anything because the answer is 0. So this is a property that allows to make easy the computation of the determinant using the property. Okay. Likewise, if you see that any row or column of the determinant have a corresponding entry are equal. Okay, in this example, I put two column 1 and column 2 identical. 1, 2, 3, 1, 2, 3. Yeah, when you see two column or two row, suppose another determinant gets 1, 2, 3, 1, 2, 3, 4, 5, 6. You detect that row 1 and row 2 is the same. The value is 0 without doing anything. And the proof is obvious. So you accept in the property number 1, when you interchange two row or two column, the sign is negative. So I change the sign. Suppose one is an area que I want to prove by contradiction que es no 0. Suppose que the answer is no 0. No 0, no 0. So when you swap column 1 and column 2, wow, it's the same determinant because they are twin brothers, no? Therefore, what is the only number que positive version is equal to the negative version? Well, is the number que have no sign, que es 0. Make sense? Suppose que the answer is 5. And this order gets given. However, when I interchange, suppose I interchange, look, suppose that you have, but the column 1 I copy here in the position 2, and the column 2 I copy in the position. Entonces I suppose que according to the property number 1, the answer would be -5. But you see, wow, something is a contradiction because this determinant is exactly the same of this. So the answer don't make different. Entonces es 0 because 0, positive 0 or negative 0 is just 0 because 0 have no sign. Okay, this is the easy way to prove by contradiction. Okay, another property is a little bit different to the matrix. A little bit, no. Very different to the matrix. Of course, we don't study matrix totally. Next lecture, we continue the matrix algebra, the matrix arithmetic, addition, subtraction, multiplication, and so on. But in the determinant, the idea is, look, let me show you. If any row or column you see the idea is repeated, it doesn't matter que es row or column. If any row or column of the determinant is multiplied by non-zero number k, arbitrary 3, 4, 5, 6, 7, -1, arbitrary pero no 0, the value of the determinant is also changed by the factor k. Example, to understand this. Let me start for this example. It's given this determinant, que the answer is 6 times 4 is 2. If you perform this row operation, in this case row operation, que the row operation according to the terminology is 3 times R1 equal R1. Entonces the conclusion is you take the row 1 original, que es 3 and 4, and multiply any entry by 3. Entonces 3 times 3 is 9, and 3 times 4 is 12. So this is the new row after the multiplication, this row 1 times 3. Well, you welcome from 3, professor. It's arbitrary number, okay? Suppose k. Suppose 3. Entonces now, when you compare the determinant and you multiply 9 times 2 is 18, and 1 times 12 is 12, and when you subtract it is 6. And notice the relationship. What is the 6? 6 is 2, que is the answer of the original, multiplied by the new factor que I introduced artificially because I want to consider 3. So in conclusion, when you have one determinant and you multiply one column or one row, it doesn't matter what one number, the value of the determinant is also multiplied by the same number. As you multiply 2, Entonces es 3 times 3 is 9. O sea, you repeat. O sea, en general es 3. You multiply 1 time. You multiply 2 times, that's 3 squared, and so on. Let's see the next example. The next example is similar, but I want to illustrate that this idea is valid not only for the row and column. You are doing now column operation. So you have again the same example. I copy again here. Look at that. And now I make a decision. I don't know why. There are no specific reason. Multiply by 2 the column 1. The column 1 original is 3 and 1. When you multiply by 2, it obtains 6 and 2. So 6 is 3 times 2 is 6, and 1 times 2 is 2. Okay. Now when and the other column, no, only multiplication, only 1. When you perform the determinant, the answer is multiplication 12 and multiplication 8, and the answer is 4, and this 4 is the multiplication 2 times 2. So this 2 gets the original value times 2 gets the factor que I select, totally arbitrary. Everyone follow me? You understand this or no? After I promise we are doing example, no? In the test, there are examples of the application for the property, no? No problema, ¿eh? Benjamin, ¿es okay? Good. Okay. Let's move into the last property. No, the last. We have more. So we have, for example, another 2 more property. Is this one? Okay, this is unbelievable, in my opinion. Okay, let me try to separate to understand more clear. Let me separate here. Let me try to make it zoom. Okay, listen. The last property say if you perform row or column operation. I never see before column operation, and the matrix only was valid row operation. To do the reduce row echelon form. But in this case, no. In this case, we are doing both row and column operation. So magically happen. I want to prove in one example, but in general happen that when you perform row operation or column operation on the determinant original, the answer stays the same. Give me the same value. It's the same value. Okay, look. Suppose one more time this example, and which the answer is 2. I don't want to repeat again. It's 2. And you perform the following row operation. 2R1 plus R2 equal capital R2. Remember, the interpretation of this is you multiply 2 times, I guess so, the element in the row 1 is 3 and 4. Look at that. 3 and 4. This and this. Plus. The element in the row 2 gets 1 and 2. And you obtain 7 and 10. And the answer we storage, you put it deposit, and this is the capital R2, that is the new one. No? Look, so 3 and 4 stay the same. I don't touch this guy. Participate in the game, but I don't touch. And 7 and 10 come from for the row operation, that row operation. Okay, now, okay. Let's compute it now. The new determinant is 30, and this is 28. And subtracting is 2. Wow, it's the same value. Unbelievable. This looks like science fiction. Okay? And same situation happen when you perform column operation. Let me try to explain column operation. Column operation. The column operation I proposed in this example was 3 times. So I select another factor. So remember the classical format for the operation is a factor. Okay, you select the row in which you have a pivot, remember, plus the other row you want to change is equal to the new row. But in this case, no. In this case, no row es column. Es column. Entonces, en the second example, es column. Let's focus see in that part. Okay, that part. I copy and paste the same example, but I want to change using this column operation. It's 3 times, it's 3 as a factor. C1 is the column 1 plus column 2 equal capital column 2. Okay, entonces 3 2 times because it's 2 by 2, I know. The column 1 is 3 1. Look at that. Plus column 2 is 2 and 4. 4 and 2, sorry. So we have 13. And we have wait. 13. And 5. Because 3 times 1 is 3. Plus 2 is 5. Now, these 3 and 5, I put in the place of the new column 2. This is capital 2, capital C2. This is a little lowercase C2, and it's a lowercase C1. And according to this operation, you obtain this new determinant. Okay, no problem. And after, I compute it using the formula. And the formula multiplication is 15. And multiplication is 13. And 15 minus 13 is 2. Exactly the same. So, conclusion. Believe it or not, when you perform on the determinant, column operation or row operation, you can apply not necessarily one, several row operation, and you transform a little bit, the value is the same of the region. Okay? This idea is clear or confused? A ver, opinion. Gustavo dice que es clear. Okay, let's move on to the next slider. What the hell is that? Next slider is the last property. Clear change. The last property. The last property is okay when you have when you have diagonals. So we have different kind of determinant. For example, so you have one determinant like that. Suppose bigger. 2, 3, 4, 5. And the main diagonal, and the rest is 0. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, and 0. This is the classical idea. And so now, this is called diagonal. Diagonal determinant. Normally we have diagonal, but we have also, well, let me explain. Diagonal is pretty easy. This is mistake. Look, this is no 0, it's 6. You fix it in the PowerPoint. Because you multiply 2 times 3, it's 6. And 0 times 0, so minus 0 is 6. It's over, right? However, in this case, no trivial. Pero es, you multiply 2 times 3 times 4. 2 times 3 is 6, times 4 is 24. Then you multiply that number, suppose 2 times 3 times 4 times 5 is 120, no? I guess so, no? 24 times 5, yeah, a 120, a 120. A 120 with I compute super easy because I don't need to apply the long formula for the cofactor. No. So you have diagonal determinant, you multiply the number in the diagonal, that's it. And also, it's not easy to prove, but you trust to me que no necessarily is complete diagonal. Suppose that we have so this determinant and this determinant have the same value. See, I fill out this 0 by arbitrary number. Suppose 10, 11, 12, 13, 14, 15. It's the same value. It's the same value. This value is totally irrelevant inside this. Look, this is the example. Okay, put a 40, 50, 80, and multiplication 2 times 3 times 4 is 24. This is let me see, this is upper diagonal. This is diagonal, pure diagonal, because it's 0 everything everywhere except in the main diagonal, and this is the lower diagonal. Okay, is, you know, and the main diagonal is 2, 3, 4, and the upper part is 0, and the lower part is arbitrary number. The value stays the same, 24. Then you take advantage of this property, because see, you can, for example, not necessarily software, such you try to do by hand, the computation of the any determinant, so you using the row operation, similar to the Gauss-Jordan elimination, but not exactly the same. You perform row operation, and you create 0 below or above the diagonal. You can compute easier the determinant. Okay. Okay. Entonces, si I summarize the property, how many property we have in total? I suppose we have 5. No? Okay. Yeah. Why we have 5? No, more than 5, 6. No. I don't know. Okay. The first one is so you interchange row or column, the determinant is change the sign. The second is, see, any column or any row is totally 0, is 0. See, two row or column are equal, is 0. If you multiply by one column or one row by one specific number, well, the new determinant is equal to the value of the original determinant multiplication by 5. We take advantage of that property, guys, to do in opposite direction, no multiplication, no factorization. So you detect things. Okay, for example, in one column or one row, we have a common factor. You can factor out. Okay. Entonces now my new determinant is easier. Therefore, I can compute it in the easy way, no? And the last property, the previous last is when you perform row operation or column operation, unbelievable, believe it or not, the value of the determinant stay the same. And take advantage of the diagonal determinant or upper diagonal or lower diagonal. Okay, it's easy because the only thing is multiplication, the number belong to the diagonal. Okay, let's practice. I bring three examples of this. Yeah, I bring 3 examples of this. Okay, this is my first example. Pretty easy, elementary, kindergarten problem. Wow, what the hell? Control C, I erase. Okay, well, okay, I don't care that part. That part is irrelevant. It's possible to remove? Yeah. Okay, cool. Escape and zoom in. Okay, this is a classical example, guys. Is an example one say if A is given, okay, A is given is one determinant. In this case, we cannot use it software because it's letter U, B, W, X, Y, Z, 1, 2, 3. Suppose that the answer of this is 4. Okay, somebody compute that. I drop to her, no problem. I need to compute a B. My question is, what is the difference between the determinant A and determinant B? Looking, using your eyes. What is the difference? Opinion, come on. What is the difference between the A determinant and B? What do you see different? They are reversed. Pero reverse who? More specific. What column, what row? The row. Okay, so the row, The row 1 and 3, no? So basically, if you have a, cool. And you perform that row operation, is row 1, swap, row 3, yes or no? You get automatically, you get B. Yes or no? Therefore, you study one property que say que when you interchange two row or two column, the answer is the same value, get 4, but opposite sign. This question mark is no question mark anymore, is negative 4. Cool? Do you understand? Using the property number 1 of the determinant. Okay, that was easy. Of course, it's easy because it's the first example. No? And I want to complicate a little bit. Let me try. All right, example 2. This is example 2. Let me make a zoom to see more clear example 2. Example 2 say wow, the determinant A is the same. It's giving S4. And you need to compute another new B. And this is a new B, somebody know me, subtracting 3 in the first column, subtracting 6 in the second column, subtracting 9 in the third column. Wow, I don't understand anything. But what is the intention? The intention is, this is a classical question, it's easy. However, I don't know why the students don't understand very well and fail in the test. Maybe I suppose that you underestimate that part. So what is the strategy? This is 2 again. The strategy is you try to manipulate using the properties of the determinant on the determinant B in order to look like similar to the matrix A. So working on this work little by little using my imagination and the property, and well, maybe the determinant B look like similarness, no, the good word, identical to the matrix A. So I like so much that I can delete mentally these 3, this 6, and this 9. Yes or no? I don't like this number because I want that this look like similar. Or similar, yeah, at the beginning similar, after identical. I need delete that. So how you delete that? Well, I propose one idea. I propose perform one row operation. Okay, 3 times R1 plus R2 and store this new information in the row 2. Well. What is the idea? The idea is when you multiply 3 times 1, it's 3. And 3 minus 3 is 0. And when you multiply 3 times 2 is 6 positive. And 6 minus 6 is 0. And when you multiply 3 times 3 is 9, positive 9, minus 9 is 0. When you perform this row operation, obviously the row 1 stays the same. Nobody touch. I using, but nobody touch. Only touch the row 2. Get definitely the answer I need. And we have here 2U, 2B, and 2W. The row 3, I don't touch. Okay? I copy exactly the same. Now, when you perform the operation, you have X, Y, and Z. Disappear. -3, -6, and -9. Everyone saw that or no? Or you need extra explanation? Huh? I am good. I understand. Gustavo. Okay, Gustavo. Now I'm using another property que say when you multiply one row or one column by a non-zero number, in this case 2, you can, so the new determinant is equal this. So you see that 2 is common here. Wow, look, I take advantage. These 2, and these 2. I factor out. So I apply the property, pero backward. You put a 2 outside. 1, 2, 3. X, Y, Z, and UBW. Wow. Okay, I know that my answer, I need to multiply by 2 because I know very well the property can say that when you multiply outside one determinant by one factor, 2 for example, you can multiply any row or any column, so you multiply 2 to 2 or 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 2 to 2. But in this case, no, I already is multiply the third row by 2, so I factor out these 2 outside. Entonces, this is a crucial moment in which this guy look like similar to this. Pero no equal, no, not yet, no? What should I do? In order to be twin brothers? What should I do? No idea? You pay attention or no? A ver, divided by 3. No, divided by 3. Okay. Please, pay attention. Pay attention que the answer is trivial. So, what is the difference between this guy? Forget about the 2 temporary and this guy. What is the difference? Very similar to the first example. Okay, the first row is 1, 2, 3. The second is X, Y, Z. And the third one is UBW, ¿no? Entonces es obvio que you interchange. A ver, eso. Gustavo say, you interchange row 2, swap row 3. When you perform this, so guy, look, we apply number 1 property 1 que you apply is this row operation. Property 2 que you apply is the factor out, and property 3 was swap 2 column, 2 row, sorry. Entonces, of course, don't forget that too, que ese factor que my original example has. No, entonces we have now 1, 2, 3 stay the same. Okay, I copy UBW here, you swap, and XYZ here. And when you interchange, what's happening? What's going on? When you interchange 2 row or 2 column, what happened? It stay the same or something change? It stay the same. So I can do is something change. No, Gustavo, something change. Change the sign. It's the first property that we study. The first property we studied. I repeat again, but you forgot. Okay, when you interchange 2 row or 2 column, the new determinant have the same value but opposite sign. Cool? Okay? Anytime. Anytime you swap 2 row or 2 column, you put a negative extra. Okay, entonces, what is the final answer of this question mark? Here. See, the original was 4. What is the answer of this? So you perform row operation, and you need to know the row operation stay the same value. So the value of this, I don't know, question mark, stay the same. You multiply by 2 here. Okay, now it's 2 times 4 is 8, no? Okay, so far we have 8. So far it's 4. Say, this is 8. But this is 4. But you swap 2 columns, so it's negative 2. So actually, negative 2 times 4 because the value of this determinant is given at the beginning, get 4, so the answer is minus 8. And minus 8, because you perform, in order to organize the problem, you are doing row operation, but I know very, very well that when you perform row operation or column operation, this new determinant is equal to the original. So this is B. This is B original. This is the B new. But this is another B new after the second operation. And this is after B new, 2B new. 3 stage. 3 stage. And the answer is negative 8 because you factor out 2 and swap 2 row is negative. Cool? Or confusing? Huh? I got it. Gustavo. And the rest, no problema. Si no comen es because you don't understand very well. Okay, we are doing one more. Example 3. I bring 3 examples. 3 examples to understand the idea behind the example 3. That one. Example 3. Example 3. I need more cooperation now in the example 3 because you understand a little bit now. A little bit, not too much. We need more practice. In the review packet, we go over again to this. So basically, I have that. I have this example, in which is given the same original determinant. This part is the same. The confusing part is the B part. The B part is you have x plus 3, y plus 6, c plus 9. This is not 93. I make a mistake here. 93, not 93. And 9. And 9. And 3w minus 1, 3b, 3w minus p, minus b or minus 2. This is 2 mistakes. And 3w minus 3. Okay. Fortunately, I have a paper, the original paper. Okay. Okay. So I can see when you're subtracting something, basically I need to perform operation. Suppose I propose you one idea. Look, one idea is you take the original. Let me copy the original one more time and without mistake. X plus 3, y plus 6, z plus 9, 3u, sorry, minus 1, 3b minus 2, 3w minus 3. Okay. And 1, 2, 3. So little by little, I think I propose you following the following row operations. Look, suppose R3, row 3, get this. 1, 2, 3, plus row 2, get this, and this new number or expression I storage in row 2. Okay, let's do it. So I don't touch the first row for a moment, and your moment may be yes, but I touch the second and the third. No, the third is the same. Participate in the game. No. Sorry. See, participate in the game. Yeah. So now when you subtracting or you addition, this positive one and negative one is cancelled. We have 3u, 3b, because it's 2 minus 2 is 0, and minus 3 plus 3 is 0, and 3w. Do you see that? Or no? Okay. And you see now that the factor 3 is common factor. You factor out. Okay, to say you factor out. 3. You put 3 outside. X plus 3. Y plus 6. C plus 9. U, B, W. 1, 2, 3. Apply the property when you multiply the determinant by a number non-zero, it's equivalent to multiply any row or any column, but we are doing backward, like a factorization. Okay? So I would be happy if I remove somehow this 3, this 6, and this 9. I need to remove this guy. How? Well, I suppose you apply row operation again. What kind? Well, it's opposite sign. This is minus 3. Suppose now on this, I want to apply the following row operation. No? It's minus 3 times row 3. Okay, row 3, remember, it's 1, 2, 3 plus row 1. This is the complicated part. You need to use an imagination, but it's easy because I want to remove 3 using 1. You multiply by -3. No? And so far we have 3. When you perform this operation and stores this new operation in row 1, it's obvious, no? Okay, the row I want to change. Entonces X, Y, Z, UBW, 1, 2, 3. Okay, entonces now in a moment take a look. My original matrix is equal 4, and you see the transformation that I should do one more time is swap who? Swap row 1, swap row 3, no? Let me see if I make a mistake. Yeah, absolutely. So 3 times, don't forget the fact to get factor out. And so now when you swap 1, 2, 3, and the first row, UBW I don't touch, and XYZ I swap to the third column, but I know very well that when you swap, you change the sign, -3. Okay, according to the property number 1. But it's giving at the beginning, get this value of the determinant F4, and 4 times -3 is -12. And this is my final answer. And the value of this determinant is given at the beginning is -12. Okay. Okay. I know that this is most not complicated, but it's the part that frequently when I teach that part, the students forget maybe. No? Okay, so let me try again here. I have 2 more sliders, but before that part, I want to explain one important part. Suppose can we try to compute by hand this determinant. 3, 4, 2, 1, -1, 5. 1, 2, and -2. Okay. Well, so now I want to use the cofactor formula. Okay. And again, I decide expand this using the first row. Guy, repetition. So you are using a different row or different column, the answer doesn't change. But then there are no too much important options. So I decide the first one. And you copy 3, gets the first entry, a multiplication by the minor determinant is formed when you delete mentally this and this. Oh, entonces 1, -1, 5, 2, and -2. Okay. So you delete mentally this, and we have a new determinant is -1, 5, 2, -2. Anyone follow me so far? Now, according to the signs of the determinant, the second one is negative. So it's -4. Remember, you copy the entry, that entry, and the corresponding value of the position of the cofactor. And now, when you delete mentally the row 1 and column 2. We have 1, 5, 1, negative 2. Okay, the second minors is 1, 5, 1, negative 2. Okay. Now plus, because the sign is plus in the last one. 2 is the entry. And the minor is, you delete mentally now, row 1 and column 3. And stay 1, negative 1, 1 and 2. Is 1, negative 1, 1 and 2. Guys, this is important. Independent that we are doing in the computer, okay, I want to explain in a few minutes this example in the computer. In Calc 3, when you take Calc 3, the student can need to take the student engineer, scientific. You need to know by hand the expansion of the determinant. Okay, let me finish. Okay, so you have 3 times, and you multiply this and this, and this and this. Be careful with the sign. When you multiply negative 1 and negative 2, it's 2. When you multiply 2 positive and 5 positive, it's 10, but you need to change the sign. Remember, this multiplication is plus, this multiplication is minus. Minus 4. Parenthesis. This multiplication is plus. So this plus do not indicate that the answer is plus. It's that we don't change the sign. So 1 times negative 2 is negative 2. And stay negative 2. However, 1 positive and 5 is a 5 positive, but you change the sign to the negative 5. Plus 2. And you multiply this and this is 2. You multiply this and this. We change the sign. Actually, double negative become positive, so 2. Guys, everyone follow me so far? Eso, bueno, Gustavo. Now we've almost finished, because 2 minus 10 is negative 8, minus 4 times negative 7, so negative 2 and negative 5 together, plus 2 times 3. Okay, we have minus 24, plus 28, because we have double negative, negative times negative is positive, plus 6. Entonces 28 minus 24 is positive 4, and positive 4 plus 6 is 10. The answer of this determinant is 10. And remember, the interpretation of this 10 maybe is the volume of the one box parallelepiped formed by the vector, que es the vector row, is this is one vector, this is another vector, and this is another vector. Okay, so I want now to using GeoGebra. Okay, remember, basically any problem 3x3, 4x4, whatever by whatever you use in computer. Only 2x2 is allowed by hand because it's pretty easy. The rest is very, very complicated. And this is just stupid arithmetic, and everyone make a mistake in this stupid arithmetic, no? I don't know. So you in one test, you are doing the homework, maybe not, but you checking, double checking, triple checking. Okay, let me try to share the screen for the GeoGebra. There you go. Guys, you need to be familiar with this. Okay, you open GeoGebra Classic, you go to the browser, create an account or no, it's your problem, and click here, and you change the view, and the classical view, no graphic anymore. We don't use them for graphic, CAS and spreadsheet. Similar to the last lecture. And you copy. You can copy in the way you prefer. You modify the width of the window, actually 3 windows. You copy in any place the number and the spreadsheet window, is look like Excel. You can copy paste whatever you want. 3, 4, 2, enter, 1, tap, -1, tap, 5, enter, change the line, 2, 1, 2, -2. It's important. Notice that this matrix is a square. Well, actually, it's not. This is not. It's just a real number, and you convert to matrix now. You select, press the right click mouse, and create matrix. Actually, now this is the most formal mathematical object is a matrix, no? Cool. And you, and the cast, que is the brain of this, you put determinant. Determinant. When you don't finish to typing, you see the word determinant of the matrix, the name of the word determinant is N1, and you press enter, and the answer, boom, este. Okay, so this is the complicated example that we're doing now. Okay, we have several matrices. Entonces you are doing this way because it's too long process. Okay, everyone follow me? Okay. Okay, Gustavo, thank you so much for your cooperation today. Well. Let's move on to the whiteboard. Switching. Okay, whiteboard. Switching to whiteboard. Do you see my whiteboard now? Okay. I want doing application. One fantastic, beautiful application is a Kramer rule. Kramer rule. It's a fantastic, you see, que in this example, que es trivial, straightforward. You don't need to do using Kramer rule. Suppose que original we have a system like that. 2 by 2. 2 equations, 1 and 2, and 2 unknown x and y. This is a line. 2 lines, chan, and you have unique solution. There are many ways to do this without matrix, without determinant. I want to illustrate the organization only of that part. And by the way, x plus y equal 8, x minus y equal 4. It's ready for elimination. You adding the equation 1 plus equation 2. If you have 2x, this part is canceled out, equal 12, divided by 2 both sides, x is 6. To find the y value using the first equation or the second, either way, it's supposed to be 6 plus y equal 8. Y alone is equal 8 minus 6 is 2. Now the point solution is the point 6, 2. We are doing in 5 seconds without Kramer rule, without determinant, without anything. However, when you have, so the point is 6, 2. I obtain using basic elimination, like elementary school or middle school. However, I want to apply Kramer rule. What is the organization Kramer rule? Pay attention now. Kramer rule, computer first. One first determinant is capital D. What is capital D? It's the determinant formed by the coefficients in from the variable. Okay, 1, 1, 1, and -1. Look at that. I did that here. That one is this. That one is this. This one is this, and this -1 is this negative. And you computed this determinant. Entonces you multiply, as always happen, this and this is -1, and this is 1, pero change the sign negative. Double -1 is negative. This is D. Okay? Everyone follow me? D? No problem with D? Now we compute it also. It's long. I know this is a disadvantage of this. However, some people, professional, prefer determinant. Okay, I respect opinion, no? Because it's more organized, more systematic, more. Okay, so now let's compute it now dx. Who is dx? One of dx is the same d, but you replace the column of the x. Remember, we have here the column of the x and the column of the y. Okay, this is the column of the x, and this is the column of the y. And you replace the column of the x by the right-hand side number. In our example, is a and 4. A and 4, and the rest stay the same. I don't touch. Only you replace this by the right-hand side, a and 4. And you compute that. And you compute that. Multiplication, a times negative 1 and negative 8. And 4 times 1. And don't forget to change the sign, and negative 4 and negative 8 and negative 4 together and negative 2. Cool. I get this negative 12. Now, dy is exactly the same, but you now replace the column of the y by the right-hand side number. Okay, this is d, que es 1 and 1, and now the column of the y, que es this column, you replace by a and 4. A and 4, this is dy, and you compute that. I did that. Look, multiplication here is positive 4, and multiplication, this is extra negative 8. Is negative 4. Everyone understand that part? Finally, the magic of the Kramer rule is que to compute x, sorry, is division dx divided by d. Systematic. X is equal dx divided by d. Y is equal, comma, dy divided by d. Suppose we have more variables. Z is equal dz divided by z, and so on. So now you divide minus 12 divided by negative 2. So you divide this divided by this, and the answer is 6. Exactly we expect at the beginning. Okay, we are solving by the student of the elementary school, middle school. 6. Now likewise, y alone is dy divided by d. Negative 4 divided by negative 2 is positive. Cool. Everyone understand very well Kramer rule? I propose you, in the short time we have after we complicate more, let's doing this. Let me explain how we can do that in the GeoGebra. So, same example, but I want to explain how you organize in the spreadsheet, how you copy paste. Look. Let's come back. Switch it to GeoGebra to explain how you manipulate easy that. Can look like horrible. No, not horrible. Do you see GeoGebra now? Cool. Now I want to delete that part. It was the last example. Yeah, I copy y now here in any place. The df1, 1, and negative 1. The fish is in front of her. Separately one, I copy the right hand side, is a and 4. A and 4. So now I want to copy this 2 times. Copy, paste. 1, 2, 3, 4. 1, 2, 3, 4 space here. Paste. And you copy the right hand side. Copy. And you replace here. Wow, this is dx, and now this is dy. Fantastic. Ready. You select You right click to create the matrix. But I want to rename. I don't want the full name N1, N2, N3. I rename. I call D. This is capital D. Okay, now likewise, I go here and you create another matrix. Here I rename DX. Likewise, you create another matrix, last one. Matrix. Here I rename like a D, Y. Rename. D, capital D, Y. Okay. Now, correct, I have 3 matrices with the corresponding name. Here we go to the cast. In the cast, you can put determiner of D, capital D. The answer was negative 2. I suppose you remember this answer, right? Likewise, determinant of the x, enter. The answer was negative 12. And the answer for determinant dy, the answer is negative 4. Okay, this is what is my x value. Well, my x value is x value. Oh, no, you can divide. This is straightforward. You divide by hand. But a more complicated scenario, okay, we are studying next time. When you, for example, you have 3 equations, 3 or no, 4 equations, 4 or no, and it's more complicated. No, the systematic way I propose you this idea. No, you put x equal, and you divide determinant dx, for example, determinant dx. I repeat again this idea. Outside the parenthesis, outside the parenthesis, division, division who? Division determinant D. Determinant, spelling wrong, determinant D. Determinant D. Pero D capital, coño. Okay, now press enter. Bang! The answer is 6. Likewise, let me copy. No, it's complicated. I copy possible. No, I don't know. Y is equal determinant dy. Automatically, you don't press enter and compute it up. Divided by determinant D, determinant, okay, D. The matrix D. And press enter now, the answer is positive. Positive 6 and again. Cool, eh? It's amazing or no? Everyone follow me or no? Eso, bueno. You dare to do at least the 3 by 3 or no? I don't know if we have time, but let me try. Let me try to do something. Not too much, maybe I don't finish, but 3 by 3, okay. 3 by 3. Let me go to the whiteboard. Okay, whiteboard. Suppose you see my whiteboard. Let me try to find this example. Where is this? This guy. Wow, complicated. Look like horrible. Look at that. Look at that. Wow, amazing. Too big. And you suppose 4x4 and 5x5 is crazy. But we have computer. And you only need to copy and paste. Okay, look at this example. I send this in the PowerPoint, guys. Suppose we have 3 equations. That one. 3 equations. And 3 unknown. X plus y minus z equals 6. 3x minus 2y plus c equals -5. X plus 3y minus 2c equals 14. Do you see the whiteboard or no? Let me know. Yes or no? No. Yes. I don't know what happened. Well, okay. Okay, this is the organization. Clear. Number 1D. Que es forme only by coefficients in from the variable. 1, 1, -1. And the first row is the first equation. 3, -2, 1 in the second equation, and 1, 3, -2 in the third equation. So for D, no participate right hand side number gets 6, -5, and 40. No. And you compare that. You expand by hand. I suppose that you understand very well this. You don't understand, no problem. We repeat it next class. And the answer is negative. Okay. Now let's move on to the dx. Dx is same D in which you replace the first column by the right hand side number 6, -5, and 40. And we compute again dx. Okay, by coincidence, it's the same value. Well, okay, nice. Now dy is exactly the same organization, but you replace now the column of the y by the right hand side number. And the answer was 99. After the computation, by hand or calculator, either way, or computer. And finally, the z. This is the same determinant, but you now replace the third column by the right hand side number. And we compute that, and the answer is positive 6. According to the Kramer rule, we already can compute x, y, and z using the formula. dx over d, dy over d, dz over d, and 1, 3, and -2, and this is my finals. I know it's long. This is not the point. The point is systematic. Everything is systematic. It's possible. Create computer algorithm to solve it easy. This. Of course, we're using the professional software. Okay, inside have the algorithm. Okay, so we take advantages. So I want to explain it again, this in the next lecture, and after we continue working with the matrix for solution for the system, but in different way. Okay, cool, no problem. Stop recording.